All right, guys, welcome to the YouTube channel. Today we're going to be talking about one-dimensional kinematics. Okay, so what is one-dimensional kinematics? Well, one-dimensional kinematics is the study of motion in only one direction. Okay, it's basically any object moving in a straight line. Okay, pretty simple. It's not worrying about how or why they move. We're just worrying about what is happening during their motion. Okay. And to kick us off, we got three main subcategories that I want to hit during this video. Okay. The first one being uh, speed. Okay. So speed is the rate at which an object covers a distance. Okay. One good thing to note about speed is that it is a scalar value. Okay. So what scalar means is that the value only has magnitude, does not have direction. Okay. So when you're in your car and you're driving, this, if you look down at the speedometer here, okay, that's a good accurate representation of a scalar, okay? Because if you just look at your speedometer, it only gives you the magnitude of your speed, how fast you're going, okay? It does not tell you what direction you're going, okay? So that is a good example of a scalar and speed in a practical form. All right, the next thing is, well, how do I calculate speed? Okay, and for us, speed is going to be the amount of distance you can cover over a certain period of time. Okay, so the formula that would be speed equals distance divided by time. Okay, when we're talking about measuring in physics, we're going to use meters for our distance, and we're going to use time. We're going to use seconds. Sorry, we're going to use seconds for our time. Okay, so knowing that, we know that the unit for speed is going to be meters per second. Okay, how many meters can I cover in a certain amount of time? A certain amount of seconds. How much speed I have. Okay, the next thing I want to talk about is velocity. Okay, let's see if I can. There we go. Okay, velocity, that is the rate at which an object covers a distance in a specific direction. Okay, oftentimes this distance is called an object's displacement. Okay, velocity, unlike speed, is a vector value. So velocity is going to have magnitude and direction. Okay, so the difference between the two in speed and velocity is velocity uses an object's displacement, whereas speed uses an object's distance. Okay, so a good example here is these two paths right here. Okay, I like to imagine this as like a track runner or something like that. Okay, so if I were to go outside and jog, and I said I jogged 3 miles, okay, well, that would be this distance track right here. Okay, notice how I said I jogged 3 miles. I didn't tell you the direction I went. I just gave you the magnitude value. Okay, so distance is the path I take, whereas displacement is the direction I go. How far in the direction I went did I get displaced from my original A point to my B point? Okay, so displacement is usually a straight line. Okay, how long did it take me to get from point A to point B? That is displacement. Okay, so it would be, if I were to say I walked 40 meters east, well, that would be displacement, because I have moved myself from 0 meters to 40 meters east of where I was. Okay, so velocity formula, very similar to speed formula. Okay, it's going to be velocity equals displacement over time. Okay, and it's going to have the same unit of measurement as speed. Okay, it's going to be meters per second. Meters per second. All right, and the third and final thing I want to talk about, or subcategory I want to talk about, is acceleration, okay? Acceleration is the rate of change in velocity, okay? So if I come down here to my acceleration example, I brought my speedometer back, okay? So acceleration would be how quickly the red indicator moves from one number to the next, okay? How quickly does that red indicator go around the speedometer, okay, during a certain period of time, okay? So it is a change in velocity. This also is a vector value, so it has magnitude and direction, okay? I accelerate in the positive direction, I'll be moving to the right or up. If I decelerate, I'll be slowing down in the negative direction, which is to the left or down, okay, depending on our coordinate system. All right, so knowing that about acceleration, we can determine that our formula here is acceleration equals the final velocity minus the initial velocity divided by time. Again, time is in seconds. These velocities and initial velocities, they will be in meters per second, okay? The unit for acceleration is going to be meters per second squared. Okay, it'll look like this right here. All right, so that's kind of just a broad overview of those three concepts in one-dimensional kinematics, going through the three broad categories. Now we're going to put what we learned into practice with some example problems here. Okay, so let me scroll down real quick. Okay. All right, so number one here, it says, let me get my pen out. Okay, use red. All right, it says a cyclist travels 600 meters in 150 seconds. What is the cyclist speed? Okay, so we want to know how fast is this cyclist going. We don't care what direction he's going, we just want to know how fast. Okay, so that's speed. All right, so we'll start with our formula, which is speed equals distance over time. Okay, now we plug in our numbers from our problem that we got, and we'll get that our distance was 600 meters and our time was 150 seconds. Okay, and y'all bear with me, this is my first time using the Wacom system over here with a pen. Okay, so if my handwriting's bad, I apologize. Okay, so I got 600 divided by 150, and that should give me 4 meters per second. Okay, that should be my final answer. That is how fast the cyclist is moving. Okay. Now, moving on, let's go to number 2. Here, let's go to number 2. Okay. All right, remember we're talking about velocity, okay? So we're worried about displacement, not distance. Okay? So let's start with our formula first, okay? Well, actually, let me read the question first. This says a person walks 40 meters east, then 10 meters west, all in 10 seconds. It's a very fast, brisk walk there, okay? What is their average velocity? All right, so our average velocity formula is going to be velocity equals displacement. That can be represented by delta x. All this triangle means is the difference in between the two x values, which is our distance. Okay, so displacement over time. Okay, so now if I plug in my numbers from our problem, now that I got my formula written, it's going to look like this. Okay, so we're going to walk 40 meters east, okay, or to the right. Then we're going to walk 10 meters back west. Okay, so I should subtract from my displacement total. Okay. So my total displacement is 30 meters east. Okay. So I was displaced 30 meters east in 10 seconds. Now I do the math and plug all those numbers in, and I should get 3 meters per second east. Okay, remember velocity is a vector, so we need to make sure we have magnitude and direction there. All right, so that's handles number 2. Okay, moving on to number 3. All right, number 3 says a car speeds up from 10 meters per second to 30 meters per second in 5 seconds. What is its acceleration? Okay, so if we remember from up top, our acceleration, pretend that's a good, let me fix this, A. There we go, that's an A. Okay, our acceleration formula is going to be our final velocity minus our initial velocity. Okay, so he speeds up from 10 meters per second, so 10 meters per second would be my initial velocity, 30 meters per second would be my final velocity. Okay, so let me go ahead and write this formula. So I'm going to just represent final velocity with V sub F. I'm going to represent my initial velocity with V sub O for original. Okay, all divided by time. All right, so if I plug my numbers in, my problem should look like this. Okay, it'll be 30 meters per second. Remember, units are important. 30 meters per second minus 10 meters per second divided by 5. Okay, remember, acceleration is just a change in velocity. How quickly did I change velocities? That is what we're looking for here. So 30 minus 10 is 20. 20 divided by 5 is going to give us 4 meters per second squared. And since our acceleration value is positive, this means that the object, or in this case a car, is speeding up in the positive direction. So either right or up, depending on our coordinate system. Okay, so that's our final answer there. Now let's go down to number 4. Okay, number 4, a train slows down from 25 meters per second to 5 meters per second in 10 seconds. What is its acceleration? Okay, so same acceleration formula as above. All right, can't write it enough. Acceleration equals our final velocity, V sub F, minus our original velocity. Sometimes if you look this up on the internet, you'll see this is V minus U. That's just V represents final velocity, U represents initial velocity. So if you ever see that out there, don't let that confuse you. Okay, V sub O, that's our initial velocity, over T, which is time. Okay, so let's plug in our numbers here. Okay, so our final velocity here is actually 5 seconds, 5 meters per second, sorry. 5 meters per second. And our original velocity is going to be 25 meters per second. All right. Okay. And then our time it took for that to happen was 10 seconds. Okay, so 5 minus 25 is going to give us negative 20 meters per second. Divided by 10 seconds, that's going to give us negative 2 meters per second squared as our final answer. Okay? So, when our acceleration is negative, that means we are slowing down, okay? And our object is moving in the negative direction, okay? So this train is slowing down 2 meters per second. Every second is slowed down by 2 meters, okay? All right, last problem here, last example problem. We'll scroll down. Okay, there we go. So, number 5 says a person jogs at a speed of 3 meters per second for 12 minutes. How far do they jog? Okay, so we're going to have to manipulate our formula a little bit here. Let's just go ahead and write the original velocity formula to start out with, okay? So we'll do velocity equals displacement delta x over time, okay? Now, if I want to solve for how far they jogged, which is delta x, all I have to do is move delta x by itself. And when I do that, I get delta x equals my velocity times my time, okay? A quick little tip here, any 3 variable formula, which is all 3 of these formulas that we learned today, you can do what I call a 3 variable triangle. So that would look something like this right here. You might have seen this in algebra. Okay, so my original formula is velocity equals delta x displacement over time. So when I have 3 variables, all I have to do if I want to solve for something different is I just cover up that block within the triangle, and that will tell me the formula in order to solve for that variable that I want. Okay, so if I wanted delta x right here, all I would do is cover it up with my finger or my thumb, and it would tell me that delta x is equal to velocity times time. Okay, so that's just a quick little tip for you. All right, now if I plug the numbers in here, I would get 3 meters per second times, remember we have to convert this to seconds, so 12 minutes converted to seconds is going to be 720 seconds. Okay, so and then 3 times 120, you would get 2,160 meters. Okay, and since it's positive, we moved in the positive direction, which is either to the right or up, depending on our coordinate system. Okay. All right, so that's it for our mathematical examples. I'm going to scroll down and we're going to talk about how to graph all of these. Okay, so the first graph I want to talk about is a position versus time graph. Okay, position versus time is going to show you how an object's position, its displacement, changes over time. Okay, this is going to help you visualize how an object moves, and we usually derive an object's velocity from these types of graphs. Okay, so let's look at a graph down here. Okay, so this graph says that every second we move 10 meters. Okay, notice how your distance is on the y-axis and your time is on the x-axis. Okay, so if we have a linear straight line like this, we are going to have a constant velocity. Okay, if I were to have a flat line right here, let's say I have a flat line at 10 meters, okay, that would mean my velocity is 0 because my position is not changing. Okay, but let's scroll down. Okay, all right, so this statement here says this graph is showing that object is moving at constant velocity. Okay, if there were a horizontal line, again, it would mean that the object has stopped moving. Okay, If I were to ask you to calculate the velocity just looking at the graph, okay, you would just look at the slope of the line, okay? The slope equals the velocity of the object. All right, so if the slope equals the velocity of the object, then I can say slope equals the difference in position, displacement, over the difference in time, okay? The time it takes. All right, so let's look here. Let's look back at our graph and see if we can't figure out how fast this object is moving. Okay, so let me do this. All right, so if I look at my graph here, the slope's the same throughout because it's a straight line, okay, linear line. All right, so we can say velocity is going to equal, all right, so we go from 0 to 1 second, we are displaced 10 meters. Okay, so we've been displaced 10 meters in 1 second. Okay, well, I just solve it like normal, and my velocity throughout this entire, at any point, you could pick out any point on the graph you see there, and it would give you 10 meters per second, okay, as the velocity of the object. All right, I could do it with our 2 right here, okay? So if I wanted to look at where the position of the object is at 2 seconds, and I wanted the velocity there, I would just plug in the numbers. So at 2 seconds, we were at 20 meters, okay? And that took me 2 seconds to get there. Okay, 20 divided by 2 is 10 meters per second. Okay, so that's our position versus time graph there. That helps us determine an object's velocity. You can determine an object's velocity without having any numbers. You can interpret the graph, find the slope, and it'll help you out. Okay, so let's move on to the next type of graph here. Okay. All right, our next type of graph is going to be a velocity versus time graph. And the main thing I want you to gather from these types of graphs is that it helps you visualize acceleration. Okay, it's going to tell you an object's acceleration, deceleration, if it has constant velocity, okay, everything like that. So let's look at a graph down here. Okay, so this is a velocity versus time graph. All right, anytime you see a linear line in a positive manner, that is going to mean that the graph, or the object, sorry, is accelerating at a constant rate, okay? The velocities are changing at a constant rate. Let me erase that right there. Erase that right there. There we go. Okay, they're accelerating at a constant rate. Now, if the line was horizontal at any point, the velocity would be constant at that point. Okay, so if it was a flat line like this, okay, at any point that would mean the velocity is constant there. Okay, which means we would have 0 acceleration because there's no change in that velocity. Okay. Now, if I want to calculate my acceleration here, slope equals acceleration. So if I want to rewrite that, I can say slope equals a difference in velocity over the difference in time. All right, so let's look at that as an example here using our graph we showed. Oop, let me erase that. Okay. Okay, let's scroll back up. There we go. Okay, so velocity versus time. Let's just pick out a point. All right, I want to know the acceleration from 1 second to 3 seconds. Okay, so what I'll do is acceleration is going to equal the change in velocity. So delta V, we can just do delta V over delta T. Okay, change in velocity over the change in time. So if I plug numbers in, if I'm looking at the acceleration between 1 second to 3 seconds, that would mean, so the velocity here at 1 second is 2 meters per second, so it would be 2. Okay, that would actually be my original velocity, so we need to put that at the end. Okay, so my velocity at there would be 2. Okay, my velocity at 3 seconds is 4. Okay, so that's my final velocity is 4. My initial velocity is going to be 2. All right. Now, the difference in time here, my final time is 3. My initial time is 1, so we have a 2-second lifespan we're talking about here. Okay, so 4 minus 2 is 2. 2 over 2 equals 1. Okay, 1 meter per second squared. So that's how we determine acceleration using a velocity versus time graph. Okay, and if you just look at the slope of the line here, you can see that for every second the velocity increases by 1, and that would match up with our answer over here that we got from our calculation. Okay, last graph of the day is an acceleration versus time graph. Okay, this is going to display how an object's acceleration changes over time. All right, this can help you work backwards to determine an object's velocity, okay, or if an object is moving with constant acceleration. Okay, so let's look at our graph. All right, so our graph here tells us that our object has no acceleration. Okay, it is a flat line at 0 for 10 seconds. Okay, so what does that mean for my velocity? Okay, this means that the object is either at rest, it's not moving at all, or that the object is moving with a constant velocity over these 10 seconds. Because remember, acceleration is a change in velocity. Okay, if there's no change, then there's no acceleration, which means it'd be 0. Okay, so that can kind of help us determine the velocities. Okay, if this line right here on the graph were up here at 0.6 rather than 0, okay, this would mean we'd have constant acceleration, all right, and our velocity versus time graph would have a line like this. We have constant acceleration, which means our velocity increases at a constant rate of 0.6, okay, for every second. Okay, so that can kind of help you work backwards to velocity versus time. I hope you found this video helpful. If you have any questions, leave them in the comments. I'll get back to you as soon as possible. And I hope you have a great day.